All right, good afternoon. Here we are yet again for another lovely session of ENGR 2302 Engineering Dynamics. So today we are moving on to chapter 17 of the Beer Vector Mechanics book, and we'll be looking at energy and momentum methods for rigid body kinetics. All right, let's begin. Okay, so again, we'll be looking at methods of work and energy and energy, work, and momentum for solving rigid body kinematics. So chapter 17, now it'll be different for, say, like a Hibbler book, but for the Beer Vector Mechanics book, it's in chapter 17. This is going to be work, energy, and momentum. For rigid body kinematics, or rigid body kinetics. For rigid body kinetics. Okay, just want to make sure we're rolling, and we are good. Okay. So we're going to use methods of work and energy, and the method of impulse and momentum can be used to solve problems of rigid bodies, just as we've used them to solve problems of individual particles, systems of particles, etc. So if you have for problems involving displacements and velocities. Involving displacement and velocity, energy methods tend to be good. Involving displacement and velocity, we tend to use our energy methods, which would be something like T1 plus U from 1 to 2 is equal to T2. Where again, T is our kinetic energy, our U is our work, and T2 is our final kinetic energy. Now, so we can use energy methods mainly for problems involving displacement and velocity. That's where they're you can use any method for anything, but they tend to be well suited for those particular types of problems. For problems involving impulse, or so for velocities in time, I should say, involving velocities in time, impulse problems or impulse methods tend to be better, or more well suited. Impulse methods tend to be better. And we'll be exploring both of these in this chapter. So, L1, if we want to remember this, for the linear momentum, would be equal to the summation of, plus the summation from the summation of the integral from T1 to T2 of f dt will be equal to L2. So basically, the original linear momentum plus the integral of the force with respect to time gives us the final linear momentum. And then for rotational systems, I can say the angular momentum one, HO1, plus the summation of the integrals of the moments from T1 to T2 of moments about some axis will be equal to the final angular momentum. So again, this looks very scary, but really what this just is the initial angular momentum plus the integral of the moment with respect to time will yield the final angular momentum. And then often these can be combined into various problems, especially for things like with eccentric impacts, that kind of thing. Okay, So continuing on. Okay, let's consider this. Let's do a bit of a review on some methods again. Overall method review. Now, if we start with, so say we're looking at a problem involving, let's look at 3 different types of problems. So one set of problems would be looking at, would have forces and accelerations, or would involve forces and accelerations. Would involve forces and accelerations. Another might involve velocities and displacements. And displacements. And another might involve velocities and time. These are different classifications of problems. And for each of these, we have different sort of analysis tools that we can use to apply to these systems. So for forces and accelerations, I'm inclined to use Newton's second law, which is what we saw in the previous chapter, or in the previous unit. So Newton's second law. Newton's second law. And this will be the summation of forces is equal to mass times acceleration. Mass times the acceleration of the gravitational center, or the center of gravity. And then the moment about the center of gravity is equal to the rate of change in the angular momentum. The rate of change in the angular momentum about the center of gravity. Then velocities and displacements can feed into, we'll use, again, methods of work and energy. We'll use methods of work and energy. And here we can simply say, well, T1 plus U from 1 to 2 is equal to T2. Where again, these aren't time, but with my capital T, I'm referring here to kinetic energy. And if I have problems of velocities and time, well, again, this is where this is really where impulse momentum theories are really shine. Impulse momentum where these really excel. And so I might have something like this. For if I'm looking at linear momentum, I might say mv1 plus the integral from t1 to t2 of f dt equals mv2. Equals mv2. And then in the case of rotational systems, I might say ig, the moment of inertia about g, times omega 1 plus the integral of the moment from t1 to t2 of mg dt is equal to ig omega 2. So this would be the moment of inertia before and after would be the same, but this would be the initial angular velocity and the final angular velocity. And this would be the initial angular momentum and the final angular momentum, and then the integral of the moment across time. All right, so next let us consider the principle of work and energy. That's what we're going to be working on today. And then also later on we can look at impulse and momentum if we have time as well. But let us consider this here. So let us look again at principles of work and energy. Again, we saw this for both individual particles and for systems of particles, and now we want to discuss this in terms of rigid body behavior. So let us look once more at the principle of work and energy. So we're going to assume that the rigid body is made of many, many particles. All right? And so we know again that work and kinetic energy are scalar quantities. So not vectors. And by assuming that they are made of many particles, we can simply add up the total kinetic energy and total amount of work performed. So by assuming the rigid body is made of many particles, we can apply the equations of particles from before. Where we will say T1 plus U from 1 to 2 is equal to T2. Where again, T1 and T2 are the initial and final, the total initial and final total kinetic energy of the particles of a body. Ke of the particles in a body and U from 1 to 2. U from 1 to 2 is the total work of internal and external forces acting on the body. Wow, that looks really bad. Running on top of myself. Internal and external forces acting on a body. So let's look at this internal versus external forces bit. Okay, so let's consider the internal work of any force on a body. Internal forces inside a rigid body, or work done by internal forces. In a rigid body. All right, so we know that if there is a general, let's look at a general potato body here. And we know that I might, maybe I have a point A here and a point B here. And maybe I have an A prime here where this whole thing is moving, and a B prime here, and a B prime here. Now, let's say there is an F here. These are two different particles, A and B, and they exert equal and opposite forces on each other, F. And then these are going to undergo some sort of change in position, which we might call, say, dr prime, something like that. Maybe dr and dr prime. So don't get hung up too much on the motions here. Well, the key is that because in translation, these forces are equal and opposite. These particles exert equal and opposite forces. Well, exert equal and opposite forces on each other. Therefore, if one ends up doing positive work, the other will do negative work. Positive work on the body then the other must do negative work. In other words, we can conclude, therefore, that the net work done by any internal force is zero. By any internal force is zero. In a rigid body is zero. Now, if this body were not rigid, that would not necessarily need to be the case. So, for example, if you had a pressure force, if I increase the, say I have a pressure vessel, and that pressure is an internal force. Well, if that pressure, if I increase the pressure, and that pressure causes a stretching of the vessel, a stretching of the metal, well, then I can actually be doing some form of work, because I am the pressure forces are stretching the metal. There is a force and a displacement relative to the center of the body. And so those forces are not immediately all canceling out. There's an energy, the shape of the object itself would be changing. The only way that internal forces can do work is if there is some change in the shape of the body itself. But since, by definition, a rigid body undergoes no kind of deformation, the internal forces cannot do any kind of work on the body. Okay. Now, let us look at another kind of thing. Let's look at some external forces. Let us look at the work done by external forces acting on a body, or acting on a rigid body. Done, or maybe just the work of forces acting on a rigid body. Okay. So let us say we have another potato object. Another lovely potato. And then let's say we have this here. Okay. Actually, I'll get to this in a bit. Let's say just in the general case, here, how might I wish to describe this? Here. Okay, so the net work done by a force. The work done, work of a force, and this is just straight out of physics class. Force during the displacement of its point of application Let's consider this. Work of a force during the displacement of its point of application. So you have a general potato body. I will draw a potato, I think, actually. One of my favorite purple potatoes. Doesn't look tasty. And so you have a point A. You're going to have some sort of point A here. And then you have a, let's say you have this kind of thing. How to label this? How do I want to label this? And you have an A and an A prime. And between them, you have an S of some sort. Let's say you have some sort of S between them. Or actually, let me show a coordinate system of some sort. Maybe X, Y. And then you could have R going to each of them. An R and an R prime to go with A and A prime. R. So initial position and final position, R prime. And U from 1 to 2, the work done from 1 to 2. Oh, and let's say there's also a force applied here. a force applied here. And so there's a force vector applied here, and the difference between the path and the force will be our alpha here. Okay, so u from 1 to 2 then, u from 1 to 2, the work done from 1 to 2 is going to be the integral from a1 to a2 of f dr. F dot dr, actually. F dot dr, or the integral from S1 to F2, S1 to S2 of f cosine alpha ds, where s is the actual path or arc length, as we've seen before.
Is the angle on the same axis as they are?
Yes, I meant that to be the same axis. Well, actually, no, just be the between. It wouldn't necessarily be the same axis as they are. It's just it's the path along the path of motion.
Okay.
It's related to the path of motion, not the path of displacement, not the path of the coordinate, the position vector. Because remember, r's are going to be position vectors. And next, let's consider this. Sorry, I keep moving forward. Then, what happens if I have, consider two forces. What if we have two forces, F and negative F, acting on a body, forming a moment M, during displacement, during a displacement at their points of application, or during the displacement of their points of application. All right, well, du is going to be equal to the change in work, the small change in work, is going to be equal to f dot dr1 minus f. Actually, let me draw this out first. I think that might help a little bit more. So again, I'll draw out a potato. I have a nice graphic for this I can draw out. So let us say I have A and B, and B, and then I have A prime and B prime. And B prime. And B prime. Here. Let's say that here. And then I could actually say maybe I had a B double prime up here as well. B double prime. So there's both a translation and a rotation going on, essentially. There's translation of A and then rotation about A. So I would have dr1 which would be the same vector. So this is our translation with A, dr1, and then a rotation about A, which produces dr2 at point B. And then this here, this angle here, would be our theta here. Would be our theta, and this might be our overall radius of rotation, r. Okay? So then du would be equal to f dot dr, dr1, minus f dot dr2, f dot dr2, plus f dot dr3, or sorry, dr2 again. Actually, this one is dr1. Sorry about that. Plus F dot dr2 here. Or this is equal to F, just F ds2, or FR d theta. FR d theta, or simply M d theta, which makes sense. It's the, for the case of a, so this is what's really useful. du would be equal to M d theta. So in the case of a couple, obviously this does make sense if you think about it. We're talking about the collapse of the overall work simply equal to the change in potential energy, the work, the small increment of work, is just going to be equal to the moment times the change in angle. That makes sense. And then u from 1 to 2 will be equal to the integral from theta 1 to theta 2 of m d theta. Of m d theta, or equal to m times theta 1, theta 2 minus theta 1, if m is constant. All right, and we will get to some quantitative problems eventually, I promise. We just need to go through our theory first. If m constant. Here. Okay, so let's think about this. All right, let us consider this. Okay, so consider something like this. Let's look at a conceptual question. Let us say I have a bar, a vertical bar, hanging from the ceiling from a pin. And there's going to be some sort of bar, there's a bar hanging here. And then there's obviously a reaction force holding this up. And then there is some sort of force P here. There's a force P here. There's a force P, and there would be some sort of, if this is point A, then there would be an AY here of some sort. Oh, and also there would have to be some sort of AX. Well, actually, no. That would be a statics problem, so we're not worrying about it being constant. But there actually might be some. I guess there might actually be some AX there. Yeah, it wouldn't be equal to the P if it was going to be accelerating, but there could still be some sort of AX there. That would make sense. But anyway, the question is. Actually, no. Never mind. I think actually AX would be equal to P, wouldn't it? It'd have to be. It would have to be, but it would not prevent rotation, but it would prevent overall translation. That would make sense. Okay, anyway, the question I have here is, which of these forces, if any, do work? Huh? It's just, well, the whole thing is a pendulum. This is just a force applied to the end of it. Which of these forces, if any, do work? Any thoughts? Which of these forces, if any, do work? Do the forces on the pin do work? Why not? Because yes, point A is exactly, point A is stationary. There is no AX and AY do no work because their point of application is stationary. Is stationary. Meanwhile, P will do work because it causes rotation of the bar. And also, these can't contribute to the rotation of the bar. Why are AX and AY prohibited from causing rotation of the bar or contributing to its rotation? Again, AX and AY, I can tell you, will not be able to cause any tendency to rotate for the bar. Why is that? Very good. Yes, the line of action of the forces passes through the pin. This is another example of constrained motion, which we saw last Tuesday. It's an example of constrained motion. So it's not able to just, if it's constrained motion, we are restricting motion to a certain axis or a certain direction, whatnot. And this thing can only rotate about the pin. So if there is any force that causes rotation about some other axis or can't cause rotation about this pin, it will cause no rotation. Let's see. Let's think about this here. Okay, so let's move on. Okay. Now let's consider this here. Let's look at kinetic energy. Let's consider some kinetic energy here. Let us look at kinetic energy of a rigid body in plane motion. Kinetic energy of a rigid body in, oh wow, that's really bad. Kinetic energy of a rigid body in plane motion. Okay. So let's draw another potato. My favorite type of fruit. No, potatoes are not fruit. I'm just seeing if y'all are awake. And X and Y. We have X and Y, and I'm going to draw another potato. As such here. And we have a particular center of gravity or centroid G here. And then I'll mention that we have an X, and I'll say we have an X prime and a Y prime axis, which are the local axes defined about the center or through the center of our potato, or if we want to be more technical, our general rigid body. X prime and Y prime here. X prime and Y prime. Now let's say this thing has a certain angular velocity, omega, lowercase omega here. And then let's say we have this. Let us look at just some point. Let us consider some arbitrary point here. It could be any points on the body. Let's just consider some point. I'll call this pi. And the I would indicate that we would be doing some sort of summation, from I, I from 1 to n type of thing. That sort of business here. And then we have, we might have this here. We would have an Ri prime. That is the radius from the point of rotation, or from the center of gravity of our particular point, pi. And this thing might have an overall velocity. We could say v. This thing might have an overall velocity v. But then it has a velocity made of two components, where velocity v bar is the velocity of the centroid, and this thing would have velocity. So again, I should say the overall velocity of this thing would be VI. The overall velocity of the global velocity of this thing would be VI. And then we also have VI prime here. And we'd have kind of a parallelogram relationship here, where the overall VI is made of components of or is a summation of the velocity of the centroid, or the center of the body, center of gravity of the body, and the relative velocity of this particle about the center of gravity of the body. Okay? So again, let me define these again, because I know that I went through that fairly quickly. V bar would be the velocity of the whole object, or the average velocity of the whole object. The VI prime, or VI, is the global velocity in XY, in the XY coordinate system. Global velocity of particle I, and VI prime, well, that would be the local velocity, or the relative velocity, of point I to the centroid, or the center of gravity. To the center of gravity. Okay, so, and I could also say, however, that VI prime could also be expressed as, because we know that there's a certain angular momentum, this relative velocity is going to be in the form of rotation. It's going to be expressed in the form of rotation about the centroid. So I could also say that VI prime is Ri prime omega. Ri prime omega. Okay, so now I could then say T, the kinetic energy, would be this 1/2 mv bar squared. So this is the energy of a particular particle. So the energy of a particular particle, let's see. So let's say the m is the mass of the entire body, and delta m, or delta mi, is the mass of particle I, of any given particle I. So then I can say that T is equal to 1/2 mv squared, mv bar squared. In other words, the global translational energy, the global kinetic energy of the entire body as a whole, plus 1/2 the summation of delta mi VI prime squared. So the summation of the individual kinetic energies about the overall, about the center of the body, VI prime squared. Or I could put this in the form of, or this is equal to the same thing, 1/2 v bar squared, v bar squared, plus the summation. I could replace this with the summation of 1/2 r prime I squared, r prime I quantity squared, times delta mi, this times omega squared. Or I could say this is equal to Another way I could write this is 1/2 m 1/2 m v bar squared plus, this also collapses to I omega, 1/2 I bar omega squared. So we can now begin to see that the kinetic energy of a system, the kinetic energy of a rigid body, is a combination of translational and rotational kinetic energies. So again, let me explicitly label this, that the kinetic energy of a rigid body, so when we were looking at individual particles, we did not say that an individual particle had rotational kinetic energy. That didn't really make much sense. An individual particle, of course, has no dimensions. It has no length, no width, no breadth. So an individual particle cannot have rotational kinetic energy. However, a rigid body can. So kinetic energy of a rigid body can be broken down into two forms. Into two pieces. One, the kinetic energy, the translational kinetic energy, kinetic energy of the, or with, associated with the motion of mass center G, and two, the kinetic energy, the rotational kinetic energy about the center of gravity, or the mass center. From the rotation of the body about the mass center. About its mass center. So then I could finally say, I could bring all this together into my a really useful equation, that T is equal to 1/2 mv squared, or mv bar squared, plus 1/2 I bar omega squared. So mass is m is the mass of the entire body. I bar is the again the moment of inertia about the centered on the mass center, and so again this all comes down to translational and rotational kinetic energies. So we have translational and rotational kinetic energies. Translational and rotational kinetic energies. Next, let us look at a system here. Let's continue on here. Next, I want to look at a case of a fixed axis. Consider a rigid body so a constrained motion again, rotating about a fixed axis through O. A fixed axis O, or through point O. So we're going to have a body that you might have something like this, and this point need not be the mass center of the body. And any object in free space will of course rotate about its center of gravity or rotate about its mass center. But I mean, if you don't have an object in free space, if you just have nailed it down to an axle, you can make something rotate however you want. well, probably not nailed down to an axle, but anyway. Okay, so we have this here. Let me write this. So we have some point O, and I'm going to have some particular pi, that's just a particle I, and then maybe I'll have Ri, which is the radius or the vector from here to here, and then I can say that this thing has a rotational velocity of omega. Omega, not omega I, just omega. The omega will be constant for the entire body. But then I have velocity vi, and this will be equal to Ri times omega. However, if I look at this in terms of some other things, well, T, we have no translational kinetic energy, so this is going to be 1/2 the summation of delta mi vi squared, which will be equal to 1/2, again, so it's the summation of basically adding up the kinetic energy of each of the individual particles. So we're saying that we have, again, I want to get back to this about a fixed axis. This is the translational kinetic energy of an individual particle. So I've just looked at its velocity here. I could say this particle just has a kinetic energy, just going in a straight line at a particular instant. But when I start summing those, when I start putting in equivalent terms, I can see that this collapses down to I omega squared. So for example, I could say 1/2, if I replace the V with R omega, I could get 1/2 delta mi times Ri omega quantity squared. Then if I distribute the square, I get 1/2 times the summation of Ri squared delta m times omega squared. But then if I group this together, I know that Ri squared delta m, hey, I've seen that before, that's moment of inertia. So this is just 1/2 times the moment of inertia about O times omega squared. So again, this is equivalent to saying, so this is equivalent to for the fixed axis, T equals 1/2 mv bar squared plus 1/2 I omega squared, I naught omega squared. Again, but let me summarize, for a body that is free, for a free body, the overall kinetic energy is going to be equal to 1/2 mv bar squared plus 1/2 I bar omega squared for a body rotating about a fixed axis. So you cannot use this equation here if you actually have a free body about a fixed axis O. Fixed axis O. Well, in that case, again, I can simply say that T is just 1/2 I-O omega squared. The only type of kinetic energy it can have is rotational. It's not allowed to translate, so it has no translational kinetic energy. All right, so I think we might go and take a short break here. I think we'll come back and look at some more theory and then maybe some quantitative examples. All right, and thank you.